Hello everyone, I'm Piotr Krzywczyński. Thank you for coming to my presentation, which is entitled Autonomous Vehicles, Bridging the Gap Between Uncertain Perception and Provably Safe Actions. This is a keynote talk at the Polish Control Conference 2020, unfortunately, given in this quite unusual remote mode because of COVID pandemic. And I hope you will enjoy this short feature. Uh, Let me define the agenda of this presentation, which is aimed at providing you with some insights about the role of perception and environment modeling and uncertainty and other aspects of perception in autonomous driving in connection to the necessity of having provably safe actions in a real world, because autonomous cars have to be safe to be really introduced to our streets. So we start with a motivation why we want to have a self-driving cars, why we have to want autonomous vehicles in different forms, starting from personal cars till city buses and short transportation modalities. As you probably know, research on autonomy of cars has started more or less in the 80s with such landmarks like CMU NavLab at the very beginning of the 90s, and then to breakthrough events organized by DARPA in 2005 and 2007. From that moment on, we really started a rise towards first autonomous vehicles, and now we have examples of real commercial autonomous vehicles like Newtonomy taxis in Singapore, some companies running pilot services with small buses in Europe as well, and also many attempts to automatize cars and other vehicles at different levels. What we want to define and to describe with this presentation are for first time differences between the necessities and possibilities we have in classic mobile robotics and in autonomous vehicles for public roads. There is a difference because we have a much more unpredictable environment in the case of autonomous driving in public roads. We no longer have this block work, which is typical for labs, for office environment, for public institutions, and generally indoor environment. Navigation, perception, localization, planning and control in outdoor settings seems to be much more complicated than those challenges we have faced in typical mobile robotics. And in such circumstances, the classic model-based methods, which were used so far successfully in computer vision, in data processing, and in general in robotics, often fail applied to massive data acquired from a number of different sensors at a very high frame rate, which is typical for autonomous vehicles on the roads. For those machines, it is typical to have a perception modules that are based on machine learning and in general on probabilistic processing, because uncertainty is something very inherent to this perception. It is also because of open and unpredictable environment. We cannot enumerate the number of states of a real world, which could be more or less the case in controlled indoor environment. So classic approaches offer some benefits like a much broader choice of the methods we can apply to ensure the formal correctness of a system design. Unfortunately, we still do not have a comparable methods for probabilistic modules, and first of all for data-driven or learnable modules. So we have to find the ways to validate the correctness of a design of a whole system to ensure safety. But we cannot rely only on classic methods, because only the data-driven approaches are able to handle this amount of data and this fast stream of data we are confronted with in autonomous vehicles, and also this setting of open world that is characteristic for real world applications. So to handle those challenges, we have to define some framework for autonomy in autonomous vehicles. So let's pose a question: how much autonomy we need in those autonomous vehicles? And first of all, what it means that we have an autonomous vehicle or autonomous driving. So on this slide, you can see some definitions for autonomous driving, also for driver assistance system, because advanced driver assistance systems are perhaps and arguably the most applicable form of partial autonomy in autonomous driving. And then how this is linked to the definition of autonomy in robotics, and in a broader sense in computer science and artificial intelligence, where we have the notion of autonomy and autonomous agents that are defined are intelligent entities operating on behalf of the owner, but without any interference of that ownership person or party. Yeah? So in a specific area of autonomous driving in automotive industry, there is a prominent organization, which is Society of Automotive Engineers, SIE in short, that established the document that defines levels of automated driving standard. We have those levels from 0 to 5, and in this classification, a higher number designates an increase in autonomy or in automation, because in this methodology, higher level of automation also means higher level of autonomy in a sense of autonomous agents. So roughly, we can define that levels starting from number 3 define autonomous systems. At the level 3, the vehicle can drive without the need for a human being to monitor and respond, but the driver has to be able to take control at all times. So he or she has to be aware what happens on the road and what happens with the vehicle. At the level 4, the systems can fully drive themselves, so without the attentiveness of a driver, but only under certain conditions. So, for example, if there is snow or there is a heavy rain or something like that, the driver has to take a control manually. At level 5, we have a full autonomy, which means that the vehicle can drive itself wherever and whenever, regardless of circumstances, regardless of day or night, regardless of weather and other circumstances like intensity of traffic. So this is a fully autonomous system, and we still do not have those fully autonomous systems. And to be honest, I'm not sure if we will have this fully autonomous system in a predictable future, because having those systems requires not only to cope with technical challenges, but also with very significant changes in law, in the legal issues. Yeah? Now let me talk shortly about some examples of autonomous cars, focusing on the sensing systems they have and the functionalities they offer to the customers. The first example is Waymo, which is a subsidiary of Google, a very famous technological corporation. And those cars rely mostly on LiDARs. So LiDAR is a short for light detection and ranging. It is like a radar, but using light instead of radio waves. So the approach from Volvo, which is a famous car manufacturer, focusing on the market of upper class vehicles, this is an example of a mixed solution. This car has cameras, has one LiDAR, and has several radars. Those radars offer the advantage of being more independent of the weather conditions than laser-based LiDARs. Yet another approach comes from Tesla, again, an iconic corporation, pioneers in electric vehicles. They automatize their cars with so-called Tesla Pilot. And this approach is mostly using passive cameras. This is very challenging with respect to the algorithms we have to apply to process data from those cameras. But on the other hand, cameras have many practical advantages. You can see that the Tesla autonomous car does not have those bulky containers on the roof. It doesn't have any protruding sensors on its chassis. It looks like a normal car. You cannot tell that this is an autonomous one. It is because cameras are compact, lightweight, energy efficient, and really cost efficient. This is perhaps the biggest advantage, because LiDAR are very expensive and also radars are pretty expensive. Cameras are much cheaper, but this comes at the cost of more challenging data processing algorithms and perhaps problems with being able to drive under any weather conditions, because at dark, at heavy rain, snow, and so on, cameras can have much more problems than a combination of LiDARs and radars. The other aspect of autonomous vehicles are advanced driver assistance systems. They are applied in cars. As you can see, we can have a similar setup of sensors like in autonomous cars, but considerably smaller level of autonomy, basically, in ADAS, we stay at level 1 of SAE autonomy. So level 1 means that we automatize only steering or speed control, not both at the same time. So we leave the decisions to the human driver. As this part of research on autonomous vehicles, I mean ADAS systems, is also very important for public transportation, because in public transportation we have more and more big electric vehicles, mostly buses. They need many drivers, and those drivers have to be skilled enough, have to be trained enough to be able to maneuver those long, often articulated vehicles, for example, during parking or during maneuvers aimed at charging their vehicles from those special electric chargers by using pantograph devices. You can see here such a pantograph proposed by a Polish Solaris bus and coach company, and also a schematic of a bus of this company. My group is collaborating with Solaris bus and coach in a project aimed at providing ADAS system for electric city buses to make it easier to maneuver those vehicles, to reduce the stress on the drivers. On this slide, you can see simple schematic of sensors and information flow in this ADAS system. Its functionalities are focused on docking to those electricity chargers, mostly using vision-based guidance, and on environment modeling and localization for maneuvers in tight spaces, like during parking among other vehicles, or in the parking lots. In this part of this ADAS system, we use mostly LiDARs that are mounted in the front and in the rear of a city bus. So now let me look closer at the perception modules that are necessary in a vehicle and on the uncertainty that is unavoidable in perception. So we, the human beings, have an enormous capability to perceive a large amount of information by using our eyes. And we can also fuse this data, and what is, I think, most important, we are able to make decisions using this multisensory input and our past experience. And this is of pivotal importance, because now and so far we have problems to implement this capability in the machines. So the machines only perceive the environment and use hard-encoded algorithms to process the data, to find some objects, to define some numerical quantities, and use them for planning and control. They do not include past experience in this process. To do that, we have to base our perception modules on learning. And one of the tasks we have to solve, we have to perform with the perception and environment modeling system is localization of a vehicle. Of course, you can say there is no necessity for localization in autonomous vehicles, because most of the scenarios go outdoors, and outdoors we have a GPS. okay, we have the GPS, but we have also a lot of problems with the GPS, because if we assume urban scenarios, then we no longer have an obtrusive view to the satellites, and we can experience a lot of problems with vanishing signals and with very big errors during localization by using any form of GPS or other satellite-based systems. So because of that, we have to use onboard sensors for localization and for other tasks like pedestrian and other vehicles and bicyclists detection, detections of any statical objects we have on the road, to avoid those obstacles, and many other subtasks. The first and most popular sensing modality for that are passive cameras. As I said before, talking about the Tesla vehicle, passive cameras have a lot of advantages, very practical advantages. There is a low cost and small size. We have also constant frame rate across the whole field of view. And what is important for driving in traffic, those sensors are passive. So we have no interference from other vehicles. However, there are also many problems with passive cameras. Mostly, they provide unsatisfactory performance in low lights and poor weather conditions. So if we want to drive at night, or if we want to drive in the rain, perhaps we have to recourse to different sensing modalities. But before we will talk about other sensors, let me show a short example of our own research that shows how important it is to have learnable modules, and how important it is to have the possibility to explain the output of this learnable module in vision-based perception. Our approach aims at detecting the electricity charges for this ADAS system I shown before on a slide in the first part of this presentation. So our approach is based on a neural network that detects those charges from a long distance, about 30 meters, because we have to have enough space, enough distance for maneuvers of a kinematically constrained vehicle, because this is for articulated buses. What is important, what is a clue of this approach, is the interpretable output of our deep neural network, which is achieved by visualization of attention heat maps. And this visualization allows us to augment the training data set with some negative examples and to improve the results. And this image explains the nature of our problem. At the very beginning, we tried to train our MUSC, our CNN, deep neural network architecture to detect the chargers. MUSC or CNN is a very popular and very powerful neural network model for classification and for detection of objects, which is very successful in computer vision. However, it was moderately successful in our application because we got a lot of false positives, so a lot of objects that actually were not electric chargers for city buses, but they were proposed by our neural model as the chargers. As you can see on this image, we have one real electric charger. This is this object that resembles a small roof in the right side of this image, and we have several false detections. Those detections appear to be on this glazed panel of a building, perhaps because of a mirrors effects, perhaps because of some similarity at the level of very low level features that are considered by our neural model. So to get rid with this problem, we had to teach our network what is not a real charger. So we augmented our neural network architecture with a possibility to have a visualization of attention maps in the form of a heat map. So in this case, the warmer colors define the regions that mostly likely contain one of the trinet classes. So in our case, there is only one trinet class, which is the electricity charger, while the cooler colors, so green, blue, and so on, they show the pixels that most likely contain only the neutral background. So they do not contain anything similar to electricity charger. And observing those heat maps, those attention maps, we were able to identify what is most often mismatched with electricity chargers. Here you can see an example. This is an image from a very famous Kitty dataset, mostly used in automotive applications for perception, for localization. It was prepared at the Karlsruhe Institute of Technology a few years ago. Now it is very popular in robotics and computer vision. Of course, this is mostly for passenger cars, and the images do not contain any electric charger. But when we used our neural model trained only with a positive examples of electric chargers, a lot of cars were mismatched with electric chargers. Also, post boxes, bus stands, and other objects were mismatched with those chargers. So we applied our explainable learning framework with the attention maps, and we observed that really this is the case. The cars and other similar technical objects generate the attention similar to electricity chargers. So we augmented our training data set with proper examples of buses, passenger cars, trucks, glazed facades of buildings, bus stands, post boxes, and other similar objects to compensate for this feature in learning. And we get much better results, as you can see on this slide. On the left side, you have the image you have already seen before with attention when the neural model was trained only by using positive examples. And on the right side, port B, you can see results of detecting the chargers when we use our augmented training data set. The augmentation was directly guided by the explanation given by those attention maps. So the results are much. A short video showing this application. As you can see, the vehicle with a camera approaches the charger from a distance, and using a classic approach to machine learning by using masker CNN, it sees a lot of false positives. And now you can see the part that was prepared using our improved model with explainable based training, thanks to this visualization of attention maps, and the results are much better. We have a clear indication where the interesting object is located. Now let me switch to the second most important sensing modality for self-driving cars and other autonomous vehicles, that are LiDARs, or laser scanners, mostly 3D laser scanners. Compared to passive cameras, they have a longer range and more accurate distance measurements. They also have a wider field of view, potentially full coverage around the vehicle, and its spatial resolution is unfortunately poorer than in cameras. So some small objects can go unattended in between the light spots projected by such a sensor, particularly at longer distances, more than 100 meters or so. So those sensors are mostly used for localization, for environment mapping, but they have to be also supported by other sensing modalities like cameras or short-range ultrasonic sensors or radars due to safety considerations. On this video, you see our approach to environment mapping by using 3D LiDAR. This is a segment-based map, so we define a planar segment and also some edges. This is a video prepared by using SICK laser scanner on a bus from Solaris bus and coach. As you can see on the images from a camera, on the video, we are going at a reasonable speed through a small town near to Poznan, mapping the environment, and obtained trajectory of our bus is similar to that one obtained from GPS. In some cases is even more accurate, because when we overlay this on OpenStreetMaps, our trajectory goes through the streets on OpenStreetMaps, while the trajectory from GPS sometimes is off-road. Another important thing in perception is semantics. In mobile robotics, we rarely needed semantics for indoor navigation, because the geometry was enough for defining the behavior of a mobile robot. This is no longer the case for outdoor and mixed environment, because in those settings we have a lot of different objects. We have also objects that have a very different and unexpected behavior. like other agents that can be encountered on the road, other vehicles, pedestrians, bicyclists, motor bicyclists, and other users of the road. And we have to identify the nature, the class of a given object to be able to predict its behavior. So we can do that using either vision or laser scanner or LiDAR data, or both at the same time, projecting the outcome of segmentation based on video data onto the 3D point clouds from a laser scanner to have classes for 3D objects that are encapsulated in boxes defining different obstacles, as you can see on this sample taken from one of the papers that are referenced at the end of this presentation. There are several different approaches to obtaining semantics in perception for autonomous driving. Classically, the segmentation or semantic segmentation was defined as maximum a posteriori estimation problem, or so-called conditional random field over the pixels, with a single pixel being considered a single field connected to other fields. And then we have to estimate the best explanation of a entire perception for a given image. Nowadays, this approach has changed. Now we have deep neural networks, mostly based on convolutional models that are considered state of the art in segmentation of images, and also applied to segmentation of point clouds from LiDARs. However, neural models still have problems with accommodation of 3D data, because images are naturally matrices that are compatible with the structure of neural networks of a convolutional type, which is not the case for 3D data that are unordered clouds of vertices. And before using a neural network that has a structure of a matrix, we have to structurize somehow those point clouds to be able to use this structure for segmentation. But it is possible with several frameworks that are available in computer vision, and also have been adapted to perception for autonomous driving. The other factor that is very important in processing of sensory data is uncertainty. There are basically two types of uncertainty in perception. The first one depends on an incoming stream of information. It's based on uncertainty in sensory data. The other one is based on uncertainty in underlying model of a process of observation. And first of all, we want to identify this uncertainty related to the real uncertainty of sensing. But the other one, called epistemic uncertainty, related to the underlying model of perception process, is also important, but it is much harder to be obtained, particularly in the case of neural models. However, there are some neural models that make it possible to obtain both types of uncertainty. An example are Bayesian neural networks, for short Bayesian deep learning methods. They adopt for neural models the Bayesian probability theory, which is acknowledged as the most useful formal language of describing uncertainty. It is commonly used in engineering and in particular in computer vision and robotics to describe and handle uncertainty. So this methodology can be also adapted for neural networks and used to obtain both kinds of uncertainty. And with this framework, we are able to identify in which areas of images or point clouds we still have to gather more information to reduce this uncertainty, or we are able to tell how uncertain are our numerical quantities we got from the neural network. There is a short example of our own research in this vein. This is a detection of key points for localization of those electricity chargers you already have seen in the previous example. So we have to have several key points to use a well-known framework from 3D vision to get localization of those objects with respect to the camera. When we have this, we can inverse this relation and obtain the location of a camera in the coordination frame of an electric charger, which is what we actually need for localization of the bus. Because the camera is rigidly attached on the bus. When we do not use uncertainty, those key points fluctuate a lot. But if we define heat maps over the detected points, what is visible on the left part of this slide, we can accurately define where these points is located, and those points no longer fluctuate on the image. And upon this information, we are also able to define the uncertainty of location of those key points on the images, which is visible in the right part of the slide, visualized in the colors from red to green, from a small uncertainty to bigger uncertainty. And this uncertainty is then propagated down the stream of equations used in localization by using uncentered transformation, and also by using classic methods of uncertainty propagation based on Jacobians. And because of that, we are able to not only localize the bus with respect to the charger, but also we are able to tell how well it is localized in terms of Bayesian uncertainty. Here you can see a video showing the process of localization. The plots in the upper right corner of the video define only the distance, because it was not possible to easily visualize 6 degrees of freedom of our pose uncertainty and the pose estimate. As you can see, the closer the camera gets to the charger, the more accurate is the localization, what is expected. Okay. When we have a defined perception processes and we have a uncertainty of this perception that can be used by other modules of a system. It could be ADAS or it could be a system for autonomous driving. Then we have to define the remaining modules, mostly responsible for planning and control of the vehicles. The planning and processes in autonomous driving can be divided into two tiers, two levels that are pretty different. The first one is coordination. So this is coordination between different vehicles on the road. Also coordination for crossing the streets or going to the crossing of streets, actually. Also coordination during making such maneuvers like takeover. The other one is motion planning itself. So once we have the coordination between different participants of a traffic on the road, then we can define the paths and then the trajectories of those vehicles. And once we have the trajectory, we can switch to lower level control. We have really a broad choice of classic algorithms used for path and trajectory planning. The most classic among them are graph search algorithms, starting from a very old but still used Dijkstra algorithm to A-star, very popular in robotics, still state lattices that are somewhat specific to vehicles, to the robots with several kinematic constraints, like a car-like vehicles. We have 4-wheel kinematics. But if we attempt to solve more complicated cases of planning with vehicles that are articulated, or with classical vehicles, but in tight spaces, like for parking or maneuvering in really crowded spaces, then we have to recurse to sampling-based planners that are probabilistic. So among them, the most known is perhaps rapidly exploring random trees algorithm proposed by Laval and Kufner. There is now a very broad family of algorithms with a lot of different modifications aimed at improving the way the states of robots or vehicle are sampled in an attempt to speed up the process of planning and to also make it more safe. The other competitive framework are probabilistic roadmaps, a little bit older, more used in industrial robots and manipulators, a little bit less popular in the area of mobile robotics, but also used for autonomous vehicles. Those probabilistic frameworks are very efficient. However, they lacked the the guarantees that are given by non-probabilistic algorithms. So those non-probabilistic algorithms have a tight guarantees, tight bounds for their performance. It can be guaranteed that an algorithm is complete in a sense that it finds the optimal way, the optimal path, or tells us that there is no path to the given goal. At the same time, the sampling-based planners only have a probabilistic boundaries, only have a probabilistic guarantees. So we can only say that in a limit, when we have a when we have a a lot of samples, then we will able to find the path. But with a limited number of samples, we are always uncertain if really the path exists or not. Besides those families of algorithms, we have also interpolating curve planners that using different mathematical frameworks to describe the curves, and along those curves, the kinematically constrained vehicles can be routed. Among those curves are clotoids, polynomial curves, Bezier curves, and also splines. Perhaps the splines and clotoids are most popular in practice in autonomous vehicles. And there is also possibility to plan the path by using numerical optimization. So we apply different constraints to the path and formulate the path search problem as an optimization problem and use a numerical algorithm to find the solution. So this is good for very constrained cases, but it's not very efficient computationally. When we have a path or a trajectory, depending on that, if we consider the time or not, then we have to execute the motion along this trajectory, this reference path. So we need a feedback controller to compute appropriate actuator inputs. Well, the role of such a controller is first of all to stabilize the reference path in the presence of vehicle modeling errors or uncertainty in modeling of the vehicle and other forms of uncertainty that can be related to perception as well. Because if we propagate the uncertainty from perception through path planning, trajectory planning, till the level of control, we are able to define boundaries along the path, the trajectory, and for example, say that as long as the controller keeps the vehicle within those boundaries, we don't need to replan the path. So if the controller is not able, it's no longer able to keep the vehicle within those boundaries, then we are out of the scope of lower level control and we have to replan the path. So this is a very important information for the control system of a vehicle. Fortunately for this low level planning, we have many effective feedback controllers that have been defined in the control theory and automation literature till now. So we can take one of them and use it to execute the reference path within the boundaries that are defined by the uncertainty. However, there is also a different approach. We can use also a learnable module to define the path for a vehicle. So we also do such research. The motivation is to provide the vehicle with a possibility to give a very rapid response to the changing scene on the road, because one of the most important characteristic of autonomous vehicles is the dynamics of changes on a scene. So as human drivers need to respond in milliseconds to what happens on the road, also the robots have to do the same. It is not always possible with classic approaches because they need sometimes several seconds to get a feasible path in response to a change on a scene. So we tried an entirely different approach. We tried a neural network to be a form of oracle, to be a form of a human memory and experience. and we learn from experience like human drivers do. So if we attempted many thousands of times to park our car in more or less the same place, we have a routine for that. We do not need to plan in advance. It is a form of reflexive behavior. So with this research, we really want to equip our vehicles in such forms of human-like reflexes. And the approach is pretty simple. We have a neural network. I will show the structure in the next slide. And we train this network with a long series of traffic situations containing the map of environment, the start point and the goal point, and a model of a vehicle. This is a four-wheeled car-like vehicle modeled after a real car. And once this network is already trained, we can give an input in the form of a single scene, in a sense of a map of environment, a 2D map of environment, and the start configuration and the end configuration. And then we obtain the resulting path from the network. Here you can see the structure of a network. As an input, we have the map, and we have the definition of a task in the form of a starting point and a goal point. And we have two parts of this network. One is a map processor. The other one is a configuration processor. The map processor processes the map to the latent representation. The configuration processes the task information, that is a starting point and the end point, also to a latent configuration. Then these latent representations are concatenated, and upon this latent representation, we estimate the required control parameters by using 4 heads that are at the output of the network. Those control parameters are related to splines that define our path that can be then easily followed by a kinematically constrained car, because it is pretty smooth and takes into account all kinematic constraints imposed by the configuration of the vehicle. Here you can see a few examples of using this neural controller, or neural path planner rather, that works as a memory of a human driver as a reflexive behavior. Basically, it's not a full, complete path planner that can plan path from point A to point B at an arbitrary distance. It is only for relatively short maneuvers, and our aim is to make it an element of a bigger system that has an upper level planner for routing, and this lower level planner for planning of individual maneuvers in response to a changing situation on the road. Here you can see that our planner is really able to respond quickly to different situations. It's also more efficient than 2 of the most typical path planners. So how we integrate all that in autonomous vehicles? Because with this part of this lecture, we are slowly approaching the most interesting part, that is how to verify all that to stay safe with actions we take in the real world. From the last part about the planning and control, you know that we have 2 approaches. One is a modular architecture, when we have separate modules that define different parts of a system related to perception, routing, coordination, path and trajectory planning, and also control. But there is also a competitive approach, which is called end-to-end driving. End-to-end driving is based on data-driven approach on learnable modules, and those learnable modules replace all that modules by a single neural network. It could be more or less complicated, and usually it does not replace all of that modules. That means that if we have to consider traffic rules, if we want to consider what happens to other vehicles at street crossing and things like that, then we still need the modular architecture. But if we just want to drive a vehicle along the roads, avoiding obstacles and considering kinematics and dynamics, we can use this end-to-end approach. The modular approach has its advantages. First of all, algorithms can be integrated upon each other, so they can be developed individually, even by different authors, different people. Sorry, which is of course an important feature for companies that want to use this approach to develop their autonomous vehicles. However, there are also pitfalls of the modular systems. Those systems are being prone to over complexity and error propagation. Of course, we want to propagate uncertainty in such an architecture, but we don't want to propagate errors. To propagate errors in the sense that if one of those modules fails, there's often no possibility to run different modules and the whole system stops. And what is really danger, there is no defined output of a system. This problem is reminiscent of the problems we had with mobile robotics architecture in the 80s. So perhaps you remember the paper of Rodney Brooks, who defined the behavior-based architecture. So those architectures were defined in response to the fallacy of sense, plan, act architectures. So the modular architectures for autonomous vehicles actually have similar problems to those sense, plan, act architectures of pretty early mobile robots, and they suffer from overcomplication. So perhaps the response is end-to-end architecture. They are simpler, monolithic, data-driven systems. They usually have only a few blocks, and the focus is shifted from mathematical modeling and developing of separate modules into gathering enough data to train a neural network that replaces those modules. However, there are pros and cons of those architectures. The pros are pretty simple. There is a non-mathematical model with often unrealistic assumptions. There is no propagation of errors over modules because it is a rather monolithic system, but there are failures possible that happen under rare, previously unseen corner cases. So those corner cases, or so-called black swans, can happen because we never are able to be sure that our system have been trained for all possible situations. This is also the case of human drivers. We, the human drivers, also often fail in very stressing, very corner situations. Yeah? But of course, there is something different to blame a human being for an accident, and it is something different to blame a machine We still do not have a proper legal framework to charge the manufacturer or the manufacturer of components with responsibility for accidents that happened when a computer was in control instead of a human being. So we have to fight against those black swan cases by two approaches, two ways. First of all is to gather good data for training, but also we need the explanation of the processes that happen inside the neural network, because end-to-end architectures are a sort of black boxes. We don't know for sure what happened inside. Here you can see an example of a road as seen by an end-to-end driving neural network. It was proposed by Mariusz Bojarski in his paper. This is also referred at the end of this presentation. And actually, this road is seen by the neural network like that. What you can see on this slide are the features in one of the layers of a neural network towards the end of this architecture. You can clearly see here elements of the boundaries of a road. This architecture was never explicitly trained to detect those particular features. It was only the matter of proper loss function and proper training data to figure out that it is important to see the boundaries of a road for the network. Yeah? But once we know what is inside the network, we are able to gather good training data. So there is a big need for explainable machine learning and in general explainable artificial intelligence in the area of autonomous driving. And when we have this, then how to verify, how to be sure that our behaviors are safe and that our propagation of uncertainty and knowledge also from the perception related modules leads to safe behaviors. As you can see, we have to train our systems on proper data, but for certification, we need a lot of driving hours, millions of driving miles to adhere to the legal regulations for driving. Only few countries have such specific regulations for autonomous cars, but they are still based on hardware tests, which could be prohibitive for manufacturers of cars, because this is extremely expensive to perform this amount of hours of autonomous driving. So with increased use of probabilistic modules and approaches in autonomous systems, these standard verification methods are no longer applicable or no longer acceptable in the economic sense. So we need a shift of paradigm in testing, including more simulation and also considering explicitly the uncertainty. So there are different frameworks for considering uncertainty. I included in this presentation two examples taking from one of the last intelligent vehicles symposiums. That one took place last year in Paris, still before the epidemic. So we were able to meet in person. So this is a probabilistic approach that ensures verification by statistical model checking. The idea is pretty simple. We define some key performance identifiers, and then we do a sufficient number of simulations to obtain a probability of meeting those performance indicators. An example of such an indicator can be, let's say, the length of braking way, so how many meters we need to stop the car from the moment we start to brake in front of an obstacle. If there is a probability, let's say 99% that we meet this criteria with a given perception and its uncertainty, which is expressed and as a Bayesian probabilistic model, then we can be sure that our system is safe. Another possibility is to use interval arithmetic. It is useful in cases we cannot express our uncertainty explicitly as a Bayesian model. In these frameworks, we also can include simulation in the loop to reduce the necessity for physical testing and the costs of verification of the system. And how we verify our neural models? There are also several frameworks that attempt to define tests for neural networks. In case of neural networks, it is most important to generate those corner cases, those black swans. If we do not have enough diversity in incoming data, then we cannot be sure that our system will react properly on such corner cases. So one of the frameworks defined to overcome this difficulty are deep tests. Also, I illustrate this with the material from a paper that is referenced at the end of the presentation. And in this case, we try to modify the real images that are acquired by a system to generate more diversified input for the system. And then on this diversified input, we could define the probability that the output is safe. So basically, that's all. And now let me conclude. I would like to conclude with a few of statements I called takeaway messages. So perhaps some of them are conclusions you consider worth to be memorized and used in your practice and in your research. I hope so. First of all, autonomous vehicle is a complicated system. It is pretty obvious, but the conclusion from this statement is that we have to check the safety and to verify also at the system level. It's not enough to verify separate components like it was enough in traditional automotive industry. This is no longer the case with autonomous driving. The other thing is that only data-driven modules, mostly based on neural networks, are able to handle the uncertainty in massive data. So we cannot avoid to use learnable modules in modern autonomous cars. So we have to have approaches to handle uncertainty from neural-based perception, and we have to have frameworks to propagate this uncertainty to planning and control modules, and then to handle properly this uncertainty at this level to take safe decision. Model-driven units are responsible mostly for low-level functions, and they have to be aware of the uncertainty of input quantities, because those quantities are uncertain in case of autonomous vehicles. The modular architectures that combine those data-driven modules and Model-driven modules are dominating the application now, and in my opinion, they will dominate in closest future, because we still are not able to obtain all necessary behaviors from a monolithic end-to-end architecture. So in those architecture, we need to provide uncertainty estimation for data-driven modules. And we need a systematic approach for checking the system safety bounds at the level of a whole system. And the last statement is about the shifting of a paradigm from mathematical models. We still need mathematical models for a control part, partially also for planning, but for perception, there is a shift of paradigm from mathematical modeling to learnable modules. But it doesn't mean that we don't need to take care about the design process. We have to do that, but we simply shift our focus from proper mathematical modeling to proper data collection. So this process of preparing the training data set has to be formalized and has to be checked to stay safe, to provide enough diversity for learnable modules. So the directions in research on autonomous driving, there are many possibilities in this area, but I think that one of the most important part is explainable artificial intelligence and machine learning. We should build modules that generate human interpretable output and estimate the uncertainty. These are two most important features for explainability. We also require new approaches to machine learning that reduce the necessity for human-labeled training data, because the errors in the training data sets are most often in human labeling. Also, we should look closer at the model-based methods, because some of them can be reused successfully with some learnable submodules. Example is deep reinforcement learning that combines reinforcement learning with models, and those models can be handcrafted by a human being, or can be modeled from data, learned from data. Also, we need new approaches to system level validation, because those example approaches I have shown you in this presentation are only examples covering sub-problems. There is still no one single approach that is accepted by the whole autonomous vehicles community, and it can serve as a golden standard for verification in this area of robotics and automation. So I also included references, mostly the papers I used to prepare this presentation. From some of them, I took also some illustrative examples to show you in this lecture. Please look closer on those few slides, and perhaps you find some of those papers interesting enough to read them in whole and use in your research. So one slide for our sponsor. I also thank my colleagues, Tomasz Nowak, Krzysztof Ćwian, Piotr Tycki, and Tomasz Gawron for helping me in preparing illustrations for this presentation. So thank you. That's all. I hope that you enjoyed this lecture. Thank you. Goodbye.